Okay, thank you very much for the introduction. And I know, Renzo, you're tired of hearing this, but I really must thank you for giving me the opportunity to be here, really. By the way, you see that Renzo is a co-author of this work. So we'll be talking about evolution of quantum knots driven by minimal surfaces. And I'd like to start with a movie of a work of 30 years ago. So this is water, and as you saw, there are two rings, okay, you see them. They have a head-on collision, and from this collision, you see the production of small rings that travel radially, and you see all these threads and bridges, and this gives you the idea of how complex classical turbulence is in viscous fluids. For this reason, those who are interested in studying turbulence prefer to play with quantum turbulence. And here, the model underneath is the Gross-Pitaevskii equation. And I reproduced the head-on collision of these two perturbed rings. Of course, I have to perturb manually. The initial condition must be perturbed, otherwise, if you have just normal rings, they will enlarge, they will slow down, and then they will fade away. In order to have the production of these small rings, you need to engineer the initial condition, I would say. So I will spend the rest of my talk trying to explain how we got here. So I will say a few words about the Gross-Pitaevskii equation, which you have already seen these days. I will show you some movies about the dynamics of some defects. We'll try to get some evolutionary scenarios from there. And then I will show you some topological quantities like right, twist, and so on. And then we'll link the dynamics of these vortices to minimal surfaces. So Gross-Pitaevskii equation, as I said, you have already seen it. This is its form. By modeling transformations, you know that you can write in terms of density of a classical fluid and velocity, which is the gradient of the phase. As I said, it's much easier to analyze turbulence in quantum context because it's localized. Vorticity is localized on the defects. We're interested in dark structures, which means that for us, the density goes to infinity and goes to 1 as you go to infinity. And so we know that if you use a spectral approach based on the fast Fourier transform, which is obviously very efficient, you need a periodic box. And if your initial condition is not periodic, you need to mirror your initial condition in all directions. And so you end up with 8 times your original degree of freedom. And this might require a lot of memory and might become a huge problem. So we had an idea just a few years ago, which was to rescale the R3 domain into -1, 1 to the third through a simple transformation. And with this idea, we can impose our initial boundary conditions at infinity without truncating the domain, basically. So the Gross-Pitaevskii equation becomes this one, and then we solve in a very efficient way by strength time splitting, and we use fourth order finite difference in space. And then, as I said, in time, we use this method, and it's splitting. So we solve we have an efficient approximation of the matrix exponential for the linear part, and then the nonlinear part is solved exactly. Just a few words about the initial condition. We know very well how to impose an initial straight vortex, which, by the way, is the only time-independent solution of the Gross-Pitaevskii equation. So if you write a new code and you want to test your code, you just put this straight vortex. And if it stays there for days, then it means that your code is good. If it moves, there's something wrong. is not the real straight vortex. Okay. Then there is another structure, which is the vortex ring, which maintain its shape. So it's a self-preserving structure which travels at constant speed. So it becomes itself in a moving reference frame. But so we know exactly how to deal with these two simple initial conditions. The problem is if you have an arbitrary initial condition like a trefoil knot, how do you generate the initial psi? Well, one idea is, given the 3D curve, by the Biot-Savart integral, you compute the velocity field, which is time-consuming, but at least you have a velocity field. Then you integrate that to get the phase, and you have to be careful. It's defined up to a constant. So you set, for instance, the phase 0 somewhere in the bulk of the domain. And then from there, you integrate, making sure to stay away from vortex defects, because then you have to end your integration either on the vortex defects or at infinity. And then we assign the density according to the fourth order Pitaevskii approximation of a straight vortex. So I show you some dynamics. This is clearly a torus knot. As you can see, there's the okay. Now we start again. So we start from the torus knot. Due to the perfect symmetry of the knot, there are 9 instantaneous reconnections that produce that blue ring. And then the secondary coiled ring, because of the same symmetries, generates 9 small rings that then move. So this is one. This one is made of 3 mutually orthogonal rings. And you see, first of all, the formation of 2 rings. You see it again. Okay, 2 rings, then just 1 loop, then 2, and then 3 again. So it reminds us of a cycle. And here we started from 2 ellipses. This is more interesting because you start from unknotted and unlinked simple geometries. And for a while, you see a hopeful link. Okay, now, okay, this is the hopeful link. And then it goes back to simple geometry. This reminds us of a cycle as well. And then I think the most interesting is this one, where well, it's very fast. I should slow it down. Where you see we start from perturbed rings, very perturbed, and you see the formation of 1 loop and then of a trefoil knot. Actually, it's more complicated. Simple loop, hopeful loop, link, trefoil knot. So this is a very interesting, we call it inverse cascade, but we'll see it later. So now let's try to classify these scenarios. I didn't show you this movie, but you start from a hopeful link, and then you get a single unknotted loop, and then from there you get 2 single loops. So this is precisely what he showed us this morning. So it's a direct topological cascade of the hopeful link. And this is one scenario. The same scenario, we put them together, and we call it collapse. For us, collapse is when there are instantaneous reconnections, so the topology changes instantaneously. And this happens only if you have very high symmetry, which in nature, of course, you don't have, but in a numerical simulation, you can. And so, as you saw in the movie earlier, you have these perturbed rings. They enlarge as they approach each other, they slow down, and because of the perfect symmetry, they reconnect at precise points, and they give rise of these radially moving small rings. So this is an example of a topological collapse. This is the torus knot 2,9. This is another example of collapse because you have very high symmetry in the initial condition, and then instantaneously a small ring, the blue one, is formed. The lighter one is very coiled, but as I said, it's perfectly symmetric. So at the same time, you have the production of 9 rings, and then these rings move away. This was the 3 mutually orthogonal rings. These are 3 rings originated by self-preserving rings. So we use that idea. And this reminds, as I said earlier, it reminds us of a cycle, structural cycle, because you start from 3 loops, unknotted and unlinked, and then you have the formation of 2 loops, then a single one, which is very long, and then from there you go back to 2, and then again 3. So it's a cycle. And this one, which is again a cycle, but it is a topological cycle because you start from 2 ellipses, and so a very simple, I mean, there are 2 planar curves, unlinked and unknotted, and from there you get for a while a half link. So there's a change in topology, but then again you go back to unlinked loops. And finally, this is something that maybe it's hard to see because we usually see the inverse. And in fact, we call it inverse topological cascade because you usually see something like this. Whereas we started from 2, as I said, very perturbed rings. And then for a while, you have the formation of a single loop. And then a half link. So there's a change in topology every time, but the complexity is increasing. And actually, in the end, we get the production of a trefoil knot. So as far as we know, this is the first realization of a topologically non-trivial knot, the trefoil knot, starting from very trivial initial conditions. So we think this is one of the main results. Now, about topological quantum hydrodynamics, well, you already seen this morning, so you know that the circulation is quantized, and the helicity is defined as the dot product between the velocity field and the vorticity field. And because vorticity is singular and on vortex lines, you get that the helicity, if you do the computation, is 0. So you have this 0 helicity condition. And as the width showed us this morning, you can write helicity in this way: the summation on all vortex lines of the self-linking number times its circulation plus the summation of linking numbers. And so what I did was to take these 4 cases. I mean, I did for many other cases, but I will show you just these plots. And for instance, if you take that knot, it evolves in time, and at every time step, I go and look for the vortex center line in order to have a 3D curve, which might be smooth enough to compute at least the first and second derivative. And then I need to compute the ribbon, because you know the twist is defined only through a ribbon. Otherwise, you cannot compute it. And by doing so, I can compute right, twist, linking number, and then helicity as the summation of all of them. So what we see here, try to concentrate on the red squares, okay? Whose scale is on the left. That's the length of the total length of the defects. And it's clear that and the dots that you see here, where the time is the time of reconnections. And you have over there the torus knot, the 3 rings, the 2 ellipses, and the 2 perturbed rings. A constant characteristic is that the length has a maximum at reconnection time. Plus, there's an asymmetry, and you can see that after reconnection, the length decreases very quickly, so its derivative is higher in absolute value than before reconnection. And this is it's a fact that is already known, and it's due to sound emission. So for this reason, reconnections are irreversible somehow. And then on the color plots are curvatures. Since there are many loops, you have different colors, and you can see that through reconnections, there is a jump in the curvature, obviously. Here, I know it's hard to see, but again, concentrate on the red squares because that's helicity. And as you can see, helicity is always constant and equal to 0. Of course, there are some errors here in that plot, but there are, because you can think that it's somehow it's difficult to get a smooth curve to do the computation of right, twist, and so on. So that's just numerical errors due to the analysis, I would say. Now, as you can see, in the first two cases, the rest of the plot is made of what? Circles, which you cannot identify in that plot, represent right, and diamonds twist. You can see that they compensate perfectly for each other. For instance, I don't know which one is which, but this one, this curve is perfectly compensated by this one to give 0. And when another loop starts, the blue one, the sum is 0. So helicity is 0. The same thing happens here, where you get a compensation of all right and twist. And so, again, your sum is 0. Now, here, with the two ellipses, at the beginning, everything seems to go as expected. But then, if you do the summation of right and twist, it's easy for you to do by eye. You get an average of minus 0.5. And as we saw earlier this morning, if you multiply by 2 the linking number, you get -1. So if you do the summation of twist, right, and linking number to get the helicity, you end up with 0 helicity. So I would, and the same is for the two perturbed rings. So I would say that the 0 helicity condition is confirmed, so the width might be, quiet. That we found a confirmation of what you showed this morning, and there is a progressive decay of right, which is a signature of a relaxing. Does it work? As long as it doesn't, yeah. So as I was saying that right is going down as a signature of relaxation towards unlinked rings. And now we talk about energy. This is the way to compute energy for the Gross-Pitaevskii equation. By Madelung transformation, you can divide in 4 contributions, which are more classical because you have kinetic energy, this new guy, which is quantum, we call quantum energy, and then you have potential energy and internal or interaction energy. Now, as you can see, if the density is almost constant, this happens just outside the vortex tubes, where density reaches the value of 1 quite quickly. The last 2 parts are just a constant contribution. And so where there is a gradient of the density, kinetic and quantum energy play a bigger role. Now, what's the link between that and minimal surfaces? There on the left, we have the Hopf link, and that is the surface of minimal area, which is an isophase surface, okay? So I take all possible isophases, surfaces, which are safer surfaces connecting these two links, these two vortices, and I compute their areas, and then I find the minimum of this area as a function of the value of theta. And so now if you consider neglecting a small region around the vortex, where density changes very quickly, you end up with a region which we call S prime minimum, which is the part of the minimum surface where density is almost constant. Then we know that from continuity equation, if density is almost constant, then the vector, the velocity field is divergence free. And since u is the gradient of the phase, you end up having the Laplacian of the phase equal to 0. But since we're looking at isophase surfaces, this means that S prime mean, which is that part of the minimal surface where rho is almost constant, is harmonic. And therefore, is critical with respect to the Dirichlet functional defined in this way. If you go and look at the Dirichlet functional where you substitute psi, you end up noticing that it's made of the two contributions, which are the kinetic energy and the quantum energy. The only difference with what we saw before is that this is an integral on the surface, it's not on the volume. So this is a 2D integral over a particular surface. And we call this, sorry, this is not a vector, it's a scalar, of course. And I use this mathematical symbol to identify the integral on the surface. And so this is just a plot to show you that in the 4 cases that I showed you earlier, the area, the minimal area changes, and in the first case of the torus knot, it decreases almost monotonically. For the 3 rings, there's a maximum in this minimum area when you have a very long loop. And then also there you have a maximum for a certain particular configuration. And whereas here, which is an inverse topological configuration, I would say cascade, you have something that changes in time. But in any case, there's definitely a link between the minimum surface and that functional, which measures the energy, because what I reported here is in blue. Just focus on the main plots. In blue, I reported that functional, which is the sum of kinetic and quantum energy. Maximum means what? That for different surfaces, I computed that functional, and then I looked at a specific time for the maximum of that functional. So max d of psi is that maximum. Whereas in for theta, the change is between 0 and 2 pi. So you have to make a lot of computations and integrals, okay? Whereas the other one is that the same functional, but computed on a specific isophase surface, which is the one of minimum area. And it's the red plot. And as you can see, they almost overlap everywhere, so they coincide. And this means that, indeed, the minimum surface is critical for the functional. So these are the conclusions. We ran direct numerical simulations of the GPE using a new code resolving the problem about a truncated domain. We identified 3 possible scenarios: direct cascade and collapse, structural and topological cycles, and the inverse cascade. The last one is, to us, the most important, because we showed that it's possible to generate a more complex structure, the trefoil knot, starting from very simple unknotted loops. We confirmed both the time symmetry, which was already known, and the zero helicity theorem. And then we saw this link between the dynamics of these defects and the minimum area. And these are just the references for this work. So thank you very much for being here.